So this is the next step forward. It's called Explore Part 1, which is a title which has gives some indication of what I'm going to talk about. Let's have a look at what I am going to do. Whoops. Now that's not working. Why is that? Hold on.
Do you want to?
Oh, there it is. It's come up now. It's okay. I'm pressing the wrong button. So I'm going to, I'm first of all going to base my talk on diagrams and a few equations from Professor Carol Haswell's standard text on exoplanet theory. And I'm going to cover quite a wide range of topics, and but desperately going to try and keep to the required time slot. So there's a rough idea of what I'm doing. I've already changed a few things in the tea break, but let's move on. So this is not quite up to date. We did get a later figure in the chat box. It was 5,206. It just goes to show, doesn't it? These things age very quickly. And transiting exoplanets, or detecting exoplanets through their transits, is by far the most prolific way of detecting exoplanets, as you can see. I've got astrometry in the list, and I put a question mark by it, or 2 question marks, because that number is likely to change quite a lot in the near future, as people who are using Gaia Data Release 3 will be coming out with their papers into the public domain. So I've just listed there the first 4 methods. I realize there are 1 or 2 other methods which one could use. In fact, Roger mentioned them, but those are otherwise the main methods. So what do exoplanets look like? Well, here they are. This is the menagerie of exoplanets. Start with the terrestrial ones, not surprisingly, Earth size, made of rock and metal. They could possess oceans, atmospheres. Ariel, of course, is going to be looking at atmospheres with transmission spectroscopy to a lot of the terrestrial type targets. Then there's the there's the super Earths on the bottom right-hand corner there. They are terrestrial in nature, but more massive than Earth, but lighter than Neptune. And they may or may not have atmospheres. Then there's the Neptune-like, the one in the middle. They are defined by being similar in size to Neptune and Uranus, and largely, we think, hydrogen and helium dominated atmospheres. And there's also a subclass called mini Neptunes, not found in our solar system, but smaller than Neptune, but larger than Earth. And then on the left-hand corner, obviously going off to the left-hand side without a complete disk, we got the gas giants, the size of Saturn or Jupiter, including, of course, the hot Jupiters, the types of exoplanet that became a very common finding in the early days of exoplanet detection, and very close to their host stars, something which at the time was considered very strange, but now good explanations are emerging. In terms of our stellar neighborhood, well, the stellar neighborhood gives you an example of the frequency of different types of star. Our sun, of course, is a G-type star. And this is worth considering when one is looking at observing transiting exoplanets, because the star itself plays a very important role in the probability of finding a transit, and indeed the quality of the transit observations. And that's just a subset of all the stars in our galaxy, for instance, within 10 parsecs. M-type stars are very common, and they're, of course, smaller than the G-type stars and also cooler. With a few exceptions, that number of exceptions is growing now that we have some new space telescopes in action, JWST. The problem with seeing exoplanets is, I think, very well documented here. If we look in the visible wavelengths, say at 500 or 600 nanometers, you can see that in arbitrary units, the radiation from the sun is 10 billion times the reflected solar radiation from these various planets in the solar system. So it's a huge ratio in the optical. And the ratio does in fact decrease if you go into the infrared, say at 10 microns, where the radiation of the sun is about 10 million times the infrared radiation from a typical planet. And we've used the solar system here as an example. So this explains why it is really very, very difficult indeed to see exoplanets either in the optical or the infrared. They are a long, long way away, and they're swamped anyway by their host stars' radiation. Well, in this case, the sun, if it was a G-type star. But we can, in fact, now image quite a few exoplanets with various techniques, and that number will increase as JWST does its thing. Oh, here we have an equation, folks. So this is one model of a planet going around a star in an elliptic orbit. We have a semi-major axis, which gives you the big dimension of the ellipse. And there is also a value called eccentricity, which tells you about the shape of the ellipse away from a circle. The simple model, the so-called classical two-body problem picture, is where the star is stationary and the planet is going around in that elliptical orbit. We call that the astrocentric coordinates, astro being probably a Greek word for star. There is an equation which can be derived for that sort of orbit, and you can see that the mass of the star, the mass of the planet, the semi-major axis of the orbit, and the period of the orbit are related by that equation. But actually, in reality, it's a different picture, which is somewhat more complicated. Here, I'm going to have to guide you around. Here is the so-called barycenter. This is the center of gravity of the star and the planet. And in order to do various types of calculation, we are going to be focusing in on the barycenter, the center of gravity of a star. And in this case, it's just a one planet system. Clearly, the picture would be a lot more complicated if you had a multiple planet system. In that picture, then, we have a planet going around the barycenter. There's the barycenter there. And we have a star also going around the barycenter, the center of mass, as you would expect. And of course, in here, the planet looks like it's actually not much smaller than the star, because the two ellipses are pretty much the same order of magnitude. Of course, in the real situation, the star's ellipse would be much smaller because it's much heavier, much closer to the center of gravity. And indeed, in most cases, the center of mass of a planetary system, a one planet system, in fact, would be inside the star, but not in the middle of the star. So here's a typical example. The sun is 99.8% of the solar system's mass, but there would still be a measurable astrometric wobble detected by an alien in the Proxima Centauri system, for instance, due to the planets and the star going around their common center of gravity. So astrometry has been fairly difficult to accomplish because it needs quite advanced optics. And it turns out to be most effective for finding high mass planets in wide orbits around nearby low mass stars. And here's an important lesson. A lot of the techniques used for detecting exoplanets turn out to be having a selection effects. They're not going to be equally able to spot all types of exoplanet in all sorts of orbits. So there's one example where astrometry comes in with that particular type of configuration. Okay, so having moved on from quite a complicated diagram, now we can look at what radial velocity measurements might do. So radial velocity measurements are essentially looking at the star, the host star of a planetary system, and looking at the Doppler shift of the absorption lines. I'm croaking up here a bit. Excuse me. I'm going to just cut my sound a moment while I have a good old cough. Better. Right. I might need a cup of tea as well. So radial velocity measurements are essentially measuring the Doppler shift of a host star in the radial direction only, for obvious reasons. We can only measure Doppler shifts in that direction. And this turns out to be a very important complementary measurement to what we all know and love, the transiting exoplanet observations. So here is the top diagram shows a well-known early planet detected. It had a period of 9.4 years. It had an eccentricity of 0.12, and we worked out that it had a mass of 0.64 mass of Jupiter. So it was indeed a hot Jupiter. The eccentricity comes out of the fact that that curve, although it might look like a sine wave, it's actually a distorted sine wave, and that level of distortion would give you a measure of the eccentricity of the planet's orbit around its host star. And we notice, of course, that the observations have error bars, even though we are capable of detecting very small shifts in the Doppler shifts of absorption lines. They still have error bars, and of course there is always the usual problem of getting the best fit curve through that data. And on the bottom we show a linearized diagram where we can see how the noise is in relation to the variation of the measurements themselves, the center of the bars in a typical measurement. That's a very early measurement taken many years ago. Just talking about naming of exoplanets, for those of you who may be new to the game, the first exoplanet discovered around any star is given the host star's name with a B after it. So you can have, say, Alpha Centauri A and a small b, and the second one is C, and so on and so on. But you'll find that is pretty well commonly followed throughout. So, there we have. Look at that, your first dynamic diagram. So this is the star's reflex orbit around the common center of gravity. There it is. There's the common center of gravity of a star and one planet. I'm only interested in one planet systems here. They're much more difficult to program if you have more than one planet, although maybe not if you use my students' new software. And of course, we're observing this system from afar. Here is the big eye at the bottom here, and you can picture that that would indeed produce a sine curve in the Doppler shift. And that's taken from a Wikipedia resource. Very useful Wikipedia. Okay, now moving on to transits then. Here is an exoplanet transiting a star as seen by us on Earth. And here is the basic parameters we need to think about are the distance of the planet from the center of the star. In this case, it could be the semi-major axis of an exoplanet, but we've simplified this to say it's say the radius of a circular orbit, and also importantly, the inclination of the stellar ecliptic plane, the equivalent of our ecliptic plane. We're going to assume that the planet is in a definite ecliptic plane. The stellar ecliptic plane is this dotted line, and the plane of the sky is the vertical line here. And we're interested in this angle, which of course will vary from stellar system to stellar system, because there is going to be no preferred direction, we think, in the ecliptic planes of stellar systems. And you can already see that transits are going to occur in certain combinations of A and I. In this particular position here, if A was very much larger off to the left here, eventually the telescope, or indeed, yes, the telescope would not see the planet coming in front of the star. And if inclination was smaller than this particular example, again, the planet would be perhaps orbiting way up here. And again, you would not necessarily see the exoplanet transiting its star. So we have to take account of the fact that the transits we're observing are in fact only a small fraction of the total number of exoplanets that we can detect, even around the systems where we have found at least one exoplanet. This is nothing new. Here is an exoplanet in this artist's conception. This is Monsieur Caro of ESA. Here is an exoplanet going in front of its host star. And this is indeed an idea that's been around a long, long time. Otto Struve, many years ago, I think it was the 1960s, said that transits of Jupiter-like planets around other stars could be detected if such planets were orbiting at favorable orbital inclinations. When we have a transit, we would expect over a typical, say, a G-type star, that the giant planet would blot out about 1% of the stellar radiation. And for terrestrial planets, that is going to go down to 0.01%. So we are looking at very small reductions in the number of photons coming from the star. But size isn't everything. We would like to know the mass of the exoplanets in addition to their radius, which we can easily calculate from measuring the dip in the light curve during a transit. That very simple equation should be easy to understand. So, look at that horrible equation in the bottom right-hand corner. Well, it so turns out that if we have the Doppler measurements of the host star, and we translate that into a velocity of the host star along the line of sight, as and the changes in that velocity with time as the one planet goes around the star, then we're going to end up with this equation, which is well defined in Carroll's book. And all I want to tell you is that if we know the I'm going to get this right. If we know the period of the planet, okay, from detecting adjacent transits of a planet in front of its star, that P there is the period of the planet. If we know the eccentricity of the planet around the star by observing the Doppler shift and noting that it's not a sine wave, it's a distorted sine wave, that will give us E. Then not worrying about the fact that the whole thing is changing with time as the planet goes around the star, we can see that we can put an upper limit on the mass of the planet, MP, we can put an upper limit, because the term MP sine I, you remember sine I from the previous diagram, the angle between the ecliptic plane and the sky plane, that is something that we can calculate if we know the mass of the star. We're assuming here that the mass of the planet will always be much smaller than the mass of the star. So in this term, in this pretty straightforward process here, we would ignore MP, and we would say, if we know M star, we know the period of the orbit, we know the eccentricity from the distortion of the Doppler curve, then we can put an upper limit on the mass of the planet, because at the moment, there's no way of us knowing about the inclination of the transit. Because we're not actually seeing a disk and an exoplanet covering that disk during its transit, we can't tell whether the transit is across the middle of the star or whether it's a grazing incidence transit across another part of the disk. So sine I, or I, is unknown for the time being, but we can put an upper limit on MP sine I by knowing the other parameters that I've just told you about, M star, P, and eccentricity. So we now have this interesting situation where, as I said before, we have selection effects. Obviously, small planets are not going to be as easy to measure the transits of than much larger planets, because this ratio and the ratio of the flux in transit and out of transit will be much smaller if you have a smaller planet. But we also now have a selection effect due to the geometric transit probability. This is the argument I developed before, where a much larger value of A in that diagram or a smaller value of I could combine together to make the transit actually not happening in front of the star, as seen by us. If you can do the mathematics, it's in Carroll's book, you'll find that the geometric transit probability is going to be R star over the semi-major axis of the planet that is in question. And that is a very important selection effect. It tells us that for all the transiting exoplanets we found so far, the 3,000 odd exoplanets from the transit method, we're only scratching the surface of what's out there, because we can't expect anything else other than random orientations of ecliptic planes. And there's going to be a selection effect from planets being relatively close to their host stars. So it gives things in context, doesn't it, to see these selection effects taking front stage. Just to remind you about the numbers, there we are. It's a little bit out of date, but the transit method is still by far the most prolific, even though we're only looking at a very small fraction of the planets that we might be able to observe in nearby stars. If we looked at the solar system from afar, using this transit probability expression, what would an alien far, far away expect to see? Well, here we have the transit probability calculated from this equation up here for our own solar system as seen from afar. And you can see that the numbers are actually quite small. Even Mercury, the most likely to be seen transiting the sun, is at a very low probability if you assume that the inclination is random, as seen by the alien some distance away. So you could argue that it's very unlikely that aliens would actually be able to see any of our planets transiting our host star. Although, of course, you could argue that there are going to be billions of aliens in our galaxy, and that one of them may just have the right view angle. I guess time will tell. So where have we got to? Here's a nice diagram, because I think this really puts things all into context now. So we have estimated the host star mass and radius from transit observations and Doppler shift. We've estimated the mass, actually sorry, I got that wrong. We've estimated the host star's mass by looking at its own spectrum. I should point that out, of course. Always we can estimate solar mass, stellar mass from knowing through our models of stars. We can give a pretty good estimate of the stellar mass. We know the radius of the planet from a typical transit observation. We can then measure the depth of the transit. Sorry, I've got that wrong again. R star, of course, is the radius of the star. So both the M star and radius of the star come from knowing the type of the star, and that gives us, through our models, both of those parameters. We measure the depth of the transit, RP. That's going to give us the radius of the planet. We can then observe an exoplanetary transit more than once and estimate its orbital period. There is a danger there, perhaps, if you look at the stellar system for long enough, you might miss one of the transits and think that the period is twice what it really is. But there are ways of working around that problem. And if you know the P, if you know the period of the orbit of the exoplanets, you can also work out its semi-major axis using that equation there. That's Kepler's third law, basically. And then from the stellar reflex Doppler shift measurements, we can place an upper limit on the exoplanet's mass, as I told you before. And then there's one more step that we can make. If we can now measure the duration of a transit, this is not something that ExoClock is particularly interested in, but if you can make an estimate of the measure of the duration of a transit from typical ExoClock type transit observations, and with a little bit of A-level geometry, you can get the equation on the bottom right-hand page, which tells us that the duration, a measurement of the duration, if we already know the period of the orbit, we know the radius of the planet and the radius of the star. The radius of the planet usually is going to be negligible with the radius of the star. We know the semi-major axis of the planet from the period that we've already calculated. We can work out what the inclination of that transit was, the inclination of the ecliptic plane, or the plane of that particular exoplanet with respect to the plane of the sky. So all these things fit together very nicely, and we can end up knowing quite a lot about the planet, its mass, its radius, its period, its semi-major axis, and its inclination to the line of sight. Quite phenomenal integration of the methods that we use or can use. So here are two typical observations. Just by pure chance, they turn out to be both from the BAA and Crayford Manor House Astronomical Society, two very prolific observers of exoplanets with their results, which have been placed in the ExoClock database. I don't think they've been finally approved, but it looks like they are very good observations and taken quite recently. And we can tell a lot from these transit curves, as well as the primary objective of ExoClock, which of course is to measure the center of the transit, which can then be used to improve the ephemerides, or is it ephemerides, and therefore update the orbital parameters of the exoplanets that are aerial targets. We can also tell a lot from the taking exoplanet transit observations in multicolors. We've already heard that briefly this morning, and there is a stylized diagram about what you might get if you had a number of different filters.
It's 12 hours.
Transit curves are flatter in the red than they are, say, in the blue and the mauve curves there. But we're not going to go into any details now. And then, as Roger, I think, mentioned quite succinctly, there's not only transits in front of their host stars, there's also the so-called secondary eclipse of the exoplanet behind the star, which gives you a whole new set of possibilities of investigating the exoplanet, including the surface temperature, maybe even different surface temperatures if the planet is phase locked, for instance, around its star. There's a whole range of new exercises which one can go after in secondary eclipses. But of course, these things are by nature generally beyond most amateurs. Most backyard telescopes would not be able to get very far with this sort of observation. But certainly telescopes within the exoclock community, quite a few of them, some of the bigger ones and better equipped ones would be able to do interesting work there. Right, on to transit timing variations. Now, this one is also perhaps a complicated diagram to start with, but let's just look at what this tells us. So with my magic pointer, here is the barycenter, the center of gravity of a star and a hot Jupiter, a big hot Jupiter. And again, I've exaggerated the distances. You would expect, even with a hot Jupiter, you would expect the center of gravity of that pair of objects to be much nearer or even inside the stylized stellar disk. But we also have terrestrial exoplanets in a wider orbit. And I haven't pretended to say that the center of gravity is the center of gravity of the whole system. I've just chosen it to be largely, that's fixed by these two much bigger objects. So in this particular situation, where the hot Jupiter is essentially, and the star are in that particular line, you would expect the exoplanet to be pulled slightly backwards from where you would expect it to be if the hot Jupiter wasn't there. And in this diagram, where the inner planet, the hot Jupiter, is in a different part of its orbit, and the star, of course, is always going to be on the opposite side of the center of gravity from the other object in that binary system, then the transiting exoplanet could end up being later in its transit, as seen from an observer on Earth. And if the exoplanet, if the inner planet, the hot Jupiter, just happens to be in line, either that configuration or 180 degrees different, then you would expect the exoplanet to be on time. So that's how the TTVs are happening. There are also other causes of TTVs. An exoplanet could be ploughing through dust and gas left over perhaps from the formation of an early stellar system. So there's a whole range of other reasons why TTVs could occur, but that is just one, and we suspect that that is going to be a method which will increasingly help us find additional exoplanets by observing the TTVs, modeling possible configurations that would cause the pattern of TTVs over a long period of time. We expect to be able to find additional exoplanets which we otherwise perhaps wouldn't be able to spot at all, possibly because they would be at a very large distance away from their star, and again having that low probability of being a transiting exoplanet. I'm going to be looking at the time. Yes, time is going quite quickly. So here is another dynamic diagram. This is the classical Jupiter system, a 4-2-1 set of resonant orbits of Io, Europa, and Ganymede. And the resonances cause these arguably otherwise circular orbits to be ever so slightly eccentric. And resonances occur, particularly strong resonances occur when the periods of orbits of, say, two planets, two exoplanets, are in a ratio like this. This is a whole number, J, so this could be, say, 2-1, or it could be, if J is equal to 2, this could be 3-2. And such resonances, so-called integral resonances, can produce particularly strong transit timing variations in any of the exoplanets that are transiting their host star. And we have the technology to do this. We have the technology now to measure TTVs to quite high accuracy, and the search for orbits which are in resonance through their signature of TTVs is surely going to be an area which is open to amateurs by analyzing data in all the databases of TTVs that we are building up. So I hope that is offering you a fairly convincing argument that this could be an interesting area for amateurs and, of course, professionals as well. Exomoons, can we go as far as detecting exomoons around exoplanets, around host stars? Well, the answer apparently is yes. This is a recent heading in Science magazine, and the first evidence is now being has now got to the level where, at least in Science Journal, they're saying may have been discovered. They're not saying it's been discovered yet. I think that takes a lot more confirmation work. But exomoons are surely going to be very interesting, because who's to say that around some of these hot Jupiters fairly close to their stars, we're not going to find equivalents of, well, Europa and Ganymede and other moons around Jupiter and Saturn, which would turn out to be particularly interesting targets if you wanted to look for life forms in our galaxy. And there's a couple of links here. I put them in various colors, but in the original PPT, which you will have access to, you can press those links and go straight to articles on the work that's being done to finally detect exomoons and have no arguments about whether it's finally discovered or not. And coming up now, just a few minutes. Oh, no, in fact, that is it. There we are. So I need to make a very grateful acknowledgement to Carol Haswell and her marvelous book, Transiting Exoplanets, which one of the audience is plowing through at the moment. And also, of course, huge thanks to Anastasia, to get the pronunciation correct, for keeping Exoclock expanding quickly in its scope and value to all sorts of people. I have several students who are going to be embarking on Exoclock projects for their Master of Science degrees. And that's a very pleasant experience to be able to introduce them to this very lively community of professionals and amateurs making very good work and strong influence on the success of future missions.
Right, thank you then, Rodney. We've got a few minutes. Siegfried, you made a couple of points on the chat. Do you want to say anything else about those so everybody can hear?
Yes, I would like to emphasize that there is a public Python code called Pandora, which has been published a few months ago, that can model exoplanet transits plus moons. So you have to you have the opportunity to download this code and start working with it.
Aha, good. Put that in the chat box. We need to find that one.
I'll download all
The
the
paper
chat.
is on archive. I will look for the link.
Yeah, very good. Thank you. We do have strong interests in
Yes,
doing some modeling and seeing whether we can use home brewed models to do some good work.
Yes, there have been some publications recently about that too. But Pandora in any case is very good already.
Open source is key.
And what we'll do, we'll download all the chat and put the comments up on the Exoplanet website where they're relevant, so everybody
Yes,
can.
you can do so. You can do so.
Right.
And have you seen Adam Rawlinson had a couple of questions? So his first question was, what was the origin of the spectral energy distribution which you showed?
Well, I mean, that is the spectral energy distribution of the sun over the optical and infrared. I could go back, actually, if you want to just look at it again. Let me just quickly go back. Doesn't take long. I can quickly go back there. Whoops, that was very quick. There we are. Right. So these are arbitrary units. So it's just to show you that the sun would be 10 billion times brighter than any of those planets there if viewed from afar. And in the infrared, say at 10 microns, the optical wavelength here is, say, what, between 500 and 600 nanometers. And this is going to be, say, 10 microns. Then you can see that in the infrared, the sun is less bright. Some planets are brighter than others, but they're all, of course, the infrared radiation given off from the hot body. So that's the infrared there. And that's going to be a much smaller ratio of brightness, but still far too much for nearly all exoplanets to be detected close to their host star. But we are beginning to see now the imaging of some exoplanets using occulting disks in front of telescopes, and JWST is doing that as we speak.
Rodney, thank you for that. My question was actually more mundane than that. It's where did that illustration come from? Because it's very nicely representing some data that is hard to find elsewhere.
Ah, okay. Well, that's in Carol's book.
Okay.
Yeah, it's a stylized diagram, but I think it does really tell the story about why we can't see anything. If we are going to see exoplanets, we need a coronagraph in front of the telescope, and the planet will need to be quite a long way away from its host star. And we are seeing a few now. Yeah.
And it's mostly working with young exoplanets.
Indeed. Yes,
Because
absolutely.
they are intrinsically bright.
Yeah.
And did you have a second question, Adam?
Yeah, I did. Rodney, you did touch on it briefly then in your presentation. Given all the data coming in, all the analysis being done, is there anything in the data to suggest a bias of the orbital planes of the exoplanets we're seeing? Specifically, orientating along the galactic disk?
Okay, I'm not aware of that. I've been using the word random, haven't I? So that would be an interesting idea to follow up. I have not come across that idea. I wouldn't be that surprised. Maybe there is some non-random distribution of stellar ecliptic planes. That would be interesting.
Because
if you want, I can jump in on that one, because I've also heard that question asked and answered. And I'm not to say that this is in any way categorically the truth, but as I understand it, they are what's been observed so far as random, but it's more not from looking at exoplanet systems as such, as protoplanetary disks as stars form.
Okay.
because then you can get a much better idea of the inclination than from, say, transits or others where they're directly observed. And I think in those cases, it's often just kind of with the infalling material from a molecular cloud as to kind of how that kind of ends up sort of being aligned and forming. But certainly I'd say, don't take necessarily my word for it, but that's what I've heard.
Interesting. Yeah,
What's
very
the
good.
solar system's inclination to the galactic plane? Anybody know off the top of their head?
No.
A lot. If you look at kind of Sagittarius and Cygnus going up in the sky, it's a reasonable. I don't know the exact number, but yeah, it's off.
Come on, Andy, you let us down. You're the tech whiz kid. Come on. Right. Okay, Rodney, thanks for that. I think we better move on to my next one.
Yeah.
Okay.
Thank you.